we're doing stem and leaf diagrams. Okay, guys, are you on stem and leaf diagrams? We've started recording. Okay. So last lesson we were doing cumulative frequency diagrams, or the snakes coming out of the toilets. They can look like that, or they can just look like regular curves, like the funny one that we made up. I think, was it this one? It came out looking like a funny, weird curve. It's a bit like a snake coming out of a toilet, but they can, by chance, come out looking like that too. It's just how the data is distributed. And we were finding the median. So to find the median, you look to see where the total is, but make sure that the graph goes up to the total. So if it finished at 70, the total would have been 70, and we would go halfway down from 70. But this time the top point in the graph matches up with 80. So you go halfway down to 80, read across and down, and there's your median. But this one asked for the interquartile range. So instead we went to 3/4 of the way down to get the upper quartile, read across and down. And showing your dot, dot, dot lines is really important. Make sure to do that in your topic assignment, to show your dot, dot, dot lines, because that's considered method mark. And 1/4 of the total in this case was 20, so read across and down. The biggest errors, as I keep going on about, is when maybe the graph actually finished here instead, but people think the total was 80. So it's wherever the graph finished that your total is, and then you read halfway down from there and across to get the median. And things like the 30th percentile, you'd work out what's 30% of the total, so 30% of 80, which we did kind of like roughly. And then you found it to be 24, because you found 10% of 80 is 8, so 30% must be 3 times 8, so 24, and then you read across and down. What would it have been? What would you say, 66? Your eyes better than mine. About 66 maybe. If you were to find, for example, the 30th percentile. So now on to stem and leaf diagrams, which was in the CIE, IGCSE kind of course. It's only one page, just brushing up on stem and leaf really. Also, I meant to show you, remember there were the pages of lessons that I said you can skip? So what I'll do is on this video, I'll just flash it up now. So anytime you want, you can go back, and if you want to do those ones, you can check your answers. So remember there were the box and whisker plot one where it was a parallel box plot, so I'll just flash it up on this video. So you know this last video is the one to go to. No, it was the previous page. So remember the parallel box and whisker plot, where was it? Must have been down here, was it? No? Oh no, it was a few pages up. Must have been down the bottom of here, was it? Yeah, there it is. I'll zoom out a bit so people can see it. 100. Okay, so this one was about the hospital, so the parallel box and whisker plot. I'm just flashing this up so that if anyone goes back and does these for practice, they can check their answers on this video. Last year. So I just snipped and pasted it in. So some were just a bit curious, what would it look like? So they had the old drug times and the new drug times. And so you would do one, doesn't matter which one you do on the bottom, which one you do on the top, just make sure to label them. So the old, notice they have the same scale, and I label the scale, drug time in seconds. So they have the same scale. So I had to make sure my scale went from roughly like 5 to 21, because that's kind of like what the results seem to go to. Which one, the old drug or the new drug, has the lower interquartile range? Which one has the lower interquartile range? Yeah, it's got a smaller box. Yep.
Do you mean like, would the question ask lower?
Yeah, that's a good point, yeah. Because interquartile range is a number. It's like the difference between something to something. Yeah, so it's just a number. So if it's lower, it means the box was closer together. That's a good question. Which one has the bigger range?
The
old drug, yeah. So which drug do you think worked faster?
The new one.
The new one, yeah. Why?
Because it means that it was a lower range of time, so it was less time it worked for.
That would probably be more a bit, that's a good point, like that might be more about the consistency. So if there's a range, that's more to do with a word called consistency or variability. But in terms of the lower, like which one had the faster times? What numbers in the blue thing could indicate the blue? You're right, the blue drug is faster, but what's a number, for example, that could indicate the blue drug? Yeah, good. That's what I was thinking of, yeah. More so the median, yeah. Because the median's like a regular kind of style value. It's a middle value. The median was lower, which meant a faster time. Yeah. But what's interesting is their minimum was higher, but the median's more like a regular kind of number, isn't it? A regular average result.
Standard deviation. in the sense of the whiskers?
Yeah, similar. Like, you know how standard deviation is the spread around the mean? These ones are the spread around the median. Yeah, so interquartile range and range are ways of measuring the spread around the median. Standard deviation measures the spread around the mean instead. So which drug had more variability? The old drug, yeah. How do you know? Yeah, bigger range. So it's got a bigger range. Max minus min is bigger, and bigger interquartile range. Yep. So less consistent. So this one was less consistent and had more variability. It had the fastest. It had the fastest results, but overall, there's probably a lot of slow ones too. It was so varied, this drug, it didn't have consistent results. So which drug do you think is more reliable? New drug, yeah. You can probably have a good idea how fast it's going to act. Whereas this old drug, it's really hard to work out how many seconds it's going to act because there's such a range of possibilities. So different ways you can interpret the box and whisker plots. So what we did for each one, I just did it on calc. So remember, you can find these things just by doing stat calc, stat edit, enter your data, and then stat calc 1 bar stats. But it's not a frequency table, so just make sure your frequency table is clear, like your frequency list is clear. And then I did that for this one, got my results, and then I did the same for this one, got my results. Because if you do stat calc, stat edit, enter the data, stat calc 1 bar stats, if you scroll down, you need to scroll down a bit to see the median, the Q1 and the Q3. The min and the max also pops up. So if you can't be bothered seeing it in your data, you can just find it this way, the min and the max. And they're the things we used, the minimum, the max, lower quartile, median, upper quartile. Then we did the same for the new drug. I plotted it together. And just set them roughly on top of each other, not touching, make sure they're not touching, and just make sure you label which one's which. Doesn't matter if I do the red one on the bottom, blue one on the top, so long as they're above the scale somewhere. So what did I say? The new drug is generally faster and more reliable, smaller range and interquartile range. The old drug has a lower minimum but a very large range, so less reliable. And overall, maybe I would say the new drug was faster. To some extent, we can argue both ways. There was also some mean questions that we skipped out because they were getting a bit repetitive. So in case anyone wants to go back and check those, it wasn't this one, it was these 2 pages. So we just reminding us how we find the mean. There's one where you had to find the midpoint. So we had a midpoint column, which you find the midpoint by averaging the outer extreme, 0 plus 50 over 2. Then the frequency fx column, frequency times the midpoint. And then do that number, that total, divide by total frequency is how you get the mean. How many in total were surveyed at 102. So if you want to do those and go back and check them, you know you can go back and check this, this page. Just a little discussion point was, why is the mean of a grouped frequency distribution table, like when the data's in groups, why is it an estimate and not the real mean necessarily?
Because you don't know the exact number?
Yeah, you don't know what, exactly, yeah. You don't know what the exact list of data was. You just know that there were 24 numbers between 100 and 150. But all 24 of those numbers could have been 105, or they could have been all different numbers. We don't know. So the midpoint is just an estimate of the scores in each class interval. The midpoint may not be the same as the other scores, and it probably wouldn't be, realistically, since one score is used to estimate all the scores in that interval. In other words, the data is grouped, which is why our calculated mean is just an estimate. We don't know the original data list. We don't know what the original real numbers were. So you can always go back and check those answers. Then there was another one, just got you to practice it again, midpoint, and then fx, total fx divided by frequency gives you the mean. The modal group just had the highest frequency. And in which class group does the median lie? Remember, you use that n plus 1 over 2 formula to find the position. We got 34.5th position. So we had to add up. So the first 17 numbers would be in this group. The next 24 numbers would be in this group. So adding them up, you haven't hit 34.5 yet. So that's going to occur in this group. And so on. So was there anything down the bottom of there? Yep, now we can go back to where we were. So that's just in case anyone wants to do those and go back and check their answers. So you can go back and check on the video anytime you want then. We're on to stem and leaf. I need to zoom in a bit, don't we? I could probably zoom a bit more. Zoom. Cool. Yep. Stem and leaf diagrams. So Ryan Gosling records a number of hits on his Twitter page over 16 days, and the following results are published. What does the number 112 mean? Yeah, that day, yeah, exactly. On his Twitter page. I don't know how those things work. Like that? Oh, would it? I probably got it wrong then. Oh well. Assume it's his YouTube channel. He's got a YouTube channel for some reason. So meant to be the number of hits. Oh really?
Yeah. 112? Are you kidding?
Okay, alright. You guys to show I would have no idea. Data.
Yeah.
Okay, let's do that.
Exactly. I just figured it was a celebrity, that's what I did.
Do you get hits on a web page as well?
Yes, I think that's what yeah, that's where you get hits.
So should we leave it as Twitter or should we say just
well, I said you should
okay,
leave it, but in reality it'll be tweets or, I mean, retweets or likes.
Oh, you listen to the right terminology.
Yeah.
Yeah. Okay, got you. Represent the data in a stem and leaf diagram. So, how many digits are allowed to be in the leaves? One. Yeah, where are the leaves? Yeah.
Wait, if the I forgot stem and leaf, not box. That the one on the left is the stem.
Yeah.
So one, it's like the one. So it was a box.
Yeah, that's right. So you can have as many digits as needed in the stem, but the leaf by definition can only have one digit. So the leaf, just by the way the rules of stem and leaves is the leaf could only be a single digit. Yeah, so you guys are picking up on the fact that, therefore, looking at the data we've got, our stems all need to be the 2 digits at the front. So what were you saying, Denise? What do you think would be the first stem? 11, yeah. And some people say if there's not a stem for 12 or something, you have to skip it. I tend to leave it in there because I think it's kind of useful to see, okay, there is no 12s, like by leaving it blank, it just communicates to you that there were no stems that had 12, or maybe they're on this one. I like to leave it in there because it communicates to the viewer, to the observer, that there were no 12s. But there were 12s in this one, was there?
Yes.
Let's do it again. 12, 13. What does it go up to? Oh, does it? Okay, nice.
So like, let's say they didn't have like a 13, would we just skip it, or would you just put it in like...
I personally like to put it in there because I think it communicates visually that there were no 13s. Whereas if you don't have it there, you've got to kind of look carefully to realise there's no 13. Because in a way, the whole point of these is to communicate the data in a more visual format. So by leaving it in there and showing that there's no leaves with it, it communicates automatically.
Just put the leaves in order.
Yeah. So some people like to do a rough version first, and then they do a neat version, but I can't be bothered. Or, yeah, or they write it really roughly over here, write it roughly on the side, and then put it neatly in there. That's another way you can do it too, rather than have to do 2 completely separate ones. Oh gosh. So I think just sort of do this. Look at what my big 11s are first, and then use something erasable. This is really getting out of calibration easy. 12, 17, 12. Yeah, 12, yep, there's 20. 20. That's just one, isn't it? 30. Yeah, so leaves have to be in order. Because okay, oh yeah, there's heaps. Yeah, 132 or not. Tell me if I'm doing it wrong. I'll have to do it again. Oh, there is! Good. I missed a 1, 2 as well. Do you see it?
Oh, there's a 1, 2, 3.
Yeah.
1, 2, 3. There's a 1, 3, 7.
Okay, so that's the next one after here, is it?
Yeah.
Okay. Yeah.
It's 1, 4, 5.
Thank you. It's probably painful watching videos really slowly.
And then 1, 5, 2, 5, 6.
2, 5, 6, yeah. So see crossing them out lightly, so you can always still see them. kind of handy. And then, like, you might, if anything, you want to check, like, if there's 16 pieces of data, there should be 16 leaves. So you could always check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now, I'm missing something. Something I used to switch on my. Is it that's a compliment? No,
Your scale, your thousand.
your
key.
Key. Yeah, that's right. Yeah, I'm missing my key. Remember those little things that we used to harass you about in year 8? So key. So you can choose any stem with any leaf. You can make up a new one if you want. You can go 13.9, 13/9. 13/9 means, does it mean 13.9?
It means 130.
Yeah, 139. If anything, do you reckon we should put 139,000 because we changed it to 1,000, didn't we?
I didn't say 1,000.
Oh, like people just thought that these numbers are really unrealistic, so we changed it to data in thousands. So you could write the number, 139,000, or the word, that kind of thing. But in a way, like, I suppose it's confusing because if that's written there, do we need it down there? It's kind of debatable. Yeah, if you think we do, then that's important.
Why can we only have one leaf if in real life there are more leaves than there are stems?
Are you talking about trees?
That's a good question.
Don't forget your key. So important.
Yeah,
There's one note on that. That's actually the word tree.
But don't
You
leaves
know.
have their own little stems?
Talking about real trees?
Yeah,
Talking
real
about
trees.
normal
That's the multiple leaves. There's just only one big
But don't leaves have their own stems?
I think she got the tree stand.
Don't worry.
So you
What are you
had an
talking
math
about?
No,
She was comparing the tree to the math leaf.
So, sorry, mine looks all stretched out and horrible. So I just can't seem to get the board to be doing nice calibration today. Okay, so what's the range? How can I calculate the range from that? The big one minus the small. Which one's the big one?
156.
Yeah, that's right. And the small one? Good, yep. So that's a great thing about it is you can visually quickly see what's the biggest, what's the smallest. So equals 156 minus 112. What does that equal?
44.
Yeah, 44.
You
Let's
write
just,
44,000.
yeah, I'm going to write 44,000.
Median.
44,000. Oh, the median. Now,
133.5.
how did you find that?
I went to the middle.
Oh, okay, yeah, true. You could kind of, because there's only 16 numbers, you could kind of count like smallest, next one, like, you know,
Yeah.
6, 5, 7, you know, that kind of stuff. Or you could use that little formula, n plus 1 over 2. So position equals n plus 1 over 2. And what's our n in this case? Yeah, 16, yeah. 16 plus 1 over 2 gives us the 8.5th position. Some people by mistake think that's a median, but it's just the position. And then we count up. So that means the average of the 8th number and the 9th number.
Yeah.
So let's count up to those. 1, 2, 3, 4, 5, 6, 7, 8, and 9. And you can probably easily see, you could show that you're averaging them, but you could probably easily see it's 133.5 thousand.
No. Oh, there's some.
No, you don't. No, you don't. You just have a paper 1 and a paper 2. Do you want one?
No.
Oh.
I really don't
I think you're missing one. No, you just have paper 1 and paper 2. Your IA is kind of like, in a sense, an investigation. But it's more in the project form. So our median is... Sorry, I'm lost in my math right now. Yeah, you have a calc and a non-calc, yeah. And it could be any topics on the calc and any topics on the non-calc. You'd probably expect a lot of, like, you know, graphing on the calculator to be on the calc. I mean, yeah, that's right. So median is we got 133.5, and then putting in thousands.
Oh.
And find the interquartile range. Hey, how would I find the interquartile range, please? How would I find the interquartile range? And how On this stem and leaf, how would you find the lower quartile? Interesting. Yeah, I'll just have to do it here. There you go.
So you treat like the first 112
Mm.
as the beginning of the bottom data set, and then that goes all the way up to 113.
Yep.
That's the first like half of the median.
Mhm.
And then you just find the median of that set right there.
Cool. And how many digits are there here? How many? How many? 8. So where?
4.5.
Yeah, 4.5. Yep. So 1, 2, 3. The 4th is here, and the 5th is here. So what's the average of 120 and 123?
121.5.
Yeah. So that's our lower quartile. So that'll be here, minus 121.5. So how would I now, as you said, Katie, find the upper quartile?
You would do the exact same thing, except for the data set from 134 to 146.
Yeah, exactly. So it'd be from here up to here. And there's 8 numbers again.
146.
Yep, so go 1, 2, 3, 4. And the 5th one here, I wanted to do that in red. To point out this is the median stuff. Yeah, so that's easy, yep, because average of 145 and 147 is just 146. And that's the upper quartile.
And you subtract the you should get 24.
Yay! So 1,000. But because we've changed it to thousands, it's complicated everything. So 24, 24, what was it?
24.5.
124.5? No, 24.5. 24.5, so 24500. Heaps. If we're putting into thousands. Any questions about those? You can get, like, you've seen back-to-back stem and leaf as well. I couldn't be bothered drawing one, so I thought I'd just show you one. These are,
Yeah, I like these ones.
yeah, they're quite cool. So, similar to like the new drug and the old drug, you could kind of like just put them back to back instead. So this half just looks like a regular stem and leaf. You've got your stem, you've got your leaves going from biggest to smallest, going from left to right. But if you do something else back to back with it, it branches out this way. So it's like you've got the stem down the center and the leaves are going from smallest to bigger as you move away from the stem. So, which is pretty normal here, and you still need to have a key. You just need to make sure it's clear which part, like this would be, for example, new drug, this could be old drug. The following, what would I say, back to beat. Oh, it was about a battery life of 2 different brands of smartphone. Are they correct in their conclusion that battery life is about the same for each phone? So that's interesting, just by visually looking at it. Yeah, what makes you think that it's around about the same?
Well, there's that chunk in the middle from like 1 to 3, which is roughly the same.
Yeah.
But
So
then there's
a lot of the data's. Yeah, that's true. That's one thing that you could argue. Yeah, there's a lot of brand B has a lot of unusually lower ones.
Higher numbers on the high side for brand A.
Ah, okay, so generally the leaves are higher.
No, I mean like 75. Like lower.
Got you. Yeah.
There are like higher numbers where the 61 is 61 and not 75.
Yeah, that's true. So you could argue some similarities in that there's a lot of the data's focused around 1, 2, or 3 stems. So like a lot of the data's because according to the key, a lot of the data's in the 10s, the 20s, or the 30s. But you could then also argue that Lauren said, that brand B has evidently more in the units, like low times, low battery lives. And brand A, it's more possible, seems to be with brand A, to have high battery lives. So you could argue a bit of both. So on one hand, yes. On one hand, yes, they are about the same. Yeah.
The lights are in that closet.
Oh, okay. Okay. Oh, you can just see it under the door, can you? I'll switch it up soon. Concentrated, a lot of the data is concentrated around the 10s, 20s, and 30s for both.
You ever finished that?
similarities. But then you can also mention, but brand B evidently has some very low ones. However,
Oh, you mean like this one? I don't think we said what they get.
more ones with
I feel like we could have done a few more.
very low battery life. I'm running out of space. So yeah, so we're kind of just pointing out, like, you know, some reasoning for why yes is in green, and some reasoning for why not entirely, though, is in red. I'm running out of space. So you can also mention, like Lauren said, brand A had a few that were quite high, whereas brand B only had one that was quite high, whereas brand 2 had 2, and so on.
What does that even say?
Where? Oh yeah, so if you're not sure what any of that's saying, feel free to let me know. And then we go into standard deviation. No, I'm gonna annoy you and leave it on. Oh no, it's been on. No. Does it switch off automatically? Oh.
Why would it switch on?
They need to have like a pilot or something, yeah. Maybe someone snuck in and hid in there this morning. Some people are just writing down this. Okay, cool. So let's go into some standard deviation. Standard deviation was kind of covered very... Oh, sorry, question. Back to you. Back to you. Yeah, no worries. So standard deviation was covered very vaguely in CIE. So we use it a bit more in IB. Like, so you'll actually probably apply it a bit more in IB and see what it means. Yeah, so before someone asked about the similarities between standard deviation and range and all that kind of thing. Range and interquartile range measures the spread of data around the median, whereas standard deviation and variance, something you might not have heard of before, measures the spread of data around the mean. Standard deviation you've learnt before, variance is just the standard deviation squared. We tend to deal with standard deviation more than we do with variance. Standard deviation is just a measure of the something of a sample around the mean. What do you think that is? Spread, yeah. So spread of data around the mean as opposed to the median.
Yeah.
Yeah, so when we're talking about interquartile range and range, we don't compare it to the mean, really. Oh, really?
Yeah.
That's interesting. Yeah, that's a good idea, because this could be done earlier, for sure. And did you all just stare blankly?
I was thinking it was hot. Like, I never heard it before.
Me either. That was the first question I would have heard of.
Yeah, so you'll get to learn a bit more now what it's about. It's a spread of data around the mean. The variance is just the standard deviation squared. So, like, you know, nothing special about it, really. Just a different way of measuring the spread is if you just square the standard deviation instead. So this is, remember, this diagram might look familiar. So, Lauren, what is the difference between a population and a sample? Again.
Just get a little further. A population is a big group. A sample is a smaller portion of that population.
Good. That's right, yeah. Population is a big group, and sample is a random selection from the population.
Snowball something?
Sample.
I used to know what my academic
Random selection from the population. Cool.
You said that?
So do you see the two different types of mean? Do you know how to pronounce this funny symbol?
Population mu.
Mu. Yeah.
That's mu.
Yeah, that's mu.
Hey,
So technically,
mu.
Yeah,
mu.
it's new. I know.
So that's mu.
There's
Mu
also
is
a
the
little,
mean.
The one with the O with the little dash. And Sophia never got math.
never come on either.
Okay, so you're at recess. Okay, so mu is the mean for a population, whereas x with the line is the mean for a sample. X is the mean for a sample. Generally, that it's the symbols we use. So there's things called population means, and there's things called sample means.
Population mean.
Yeah, population means the mean of all of them, the big group. Sample mean means the mean of the little sample that you randomly selected from the population. Oh, so we're just recapping on population, sample. X is the mean from a sample. Mu is the mean from a population. Oh, yeah. So this is very stat edity, what we're doing. Your GDC will give you two different means. You probably noticed that when you used to do stat edit and find the standard deviation. Oh, sorry, we'll give you two different standard deviations, sorry. One is for the standard deviation of a population. That's the one that you used in CIE, isn't it? Let's put a big yellow circle on that, baby. Because this is the one we use as well. We deal with this one. You just need to know the difference between the two. But if we're asking for the standard deviation, we're generally asking for the population one. So this, what's the name of this funny little symbol?
Open constant.
It's called sigma. Sigma is the name of that letter. Greek letter. Sigma. So that's one we use from the calculator, and the other one is the standard deviation for a sample. So we use the standard deviation for a population, is our most popular one. So I think the most popular one is the standard deviation for a population, but it's the same one as you used in CIE. You ignore the S of X, mainly for our ones. But you might just need to refer to those kind of things in an IA, I don't know. In our course, we only consider the standard deviation for a population, the sigma one, which both of them can be found on the GDC, but we use the sigma version. So to find the standard deviation, just like before, you go stat edit, enter your data into L1. If it's a frequency table, then you need to put it into L1 and L2 instead. Then you do stat calc 1 var stats. Your X list should just say L1 if it's just a single list of numbers. If it's a frequency table, don't forget to tell it that frequency is L2 as well. And then, yeah, so stat calc 1 var stats, and then the stuff will come up. Then you'll see standard deviation of the population will pop up. Will be one of them. The formula for doing it by hand, if you do it in an IA, you might need to do it by hand. This is what the calculator is doing for you. What does that funny big symbol mean? The sum of, yep. What's that little mu again?
It means population.
Yeah, that's right. And what do you think the N is?
Number of?
Yeah, number of things in your data set. Yep, number of items. So that's the population mean, which is just the mean of the population.
What's the thing under the X sigma?
It was equal to.
I think it's I equals 1. Meaning starting with 1, the first term. This one?
No, the one there.
I think so. What is it? I can't see it on yours.
That looks like X.
Oh, it's cut off on yours, is it?
Yeah.
It comes from your textbook. Does anyone? I could open it up on the textbook. Do I have the textbook here? So I snipped this from your textbook. Let's see what it is, so you can write it in properly. That's like sigma notation, isn't it? Standard deviation. No, that's not it. What chapter is this stuff in? Chapter 6?
I think it's chapter 8.
Chapter 8. Oh, thank you. You are right. Okay, standard deviation. Getting to the bottom of this formula for you. Almost there. Variance and where is it? Oh, here it is. Oh, my eyes can't even see. It's an N. So Owen, this little baby up here is an N.
Okay. What's the thing below it?
It's an N.
That's an N.
What's the thing below it?
The thing below it is a I equals 1.
What is it?
Nah.
You wrote an N on top of the sigma?
I equals 1, like that kind of thing. Yeah, like what that thing is, this little symbol that's got kind of blurred out, it's an N. N standing for, like, you know, you go all the way up to N. And I equals 1 meaning you start with
I
1.
equals 1?
Yeah. Yeah.
So like imaginary?
No. Just meaning that the first thing you start with is the first. You start with the first term. So N means the number of items in the data set.
Oh, this is really
In a data set.
What does I equals 1?
I just mean you start with the first. Like remember sequences and series, if I equals 2 means you start with the second. Starting with 2. Very vaguely. So basically what you do, if you were to do it by hand, imagine there were six numbers in your data set. What you would need to do is you'd need to do each number, you need to calculate the mean first of the 6 numbers, and each number minus the mean, and then you would square that result, and then take the second number minus the mean, square that result, take the third number minus the mean, square the result until you get up to all the numbers, add all that together, and divide by 6. That's how you would do it by hand, and then the square root of that. I forgot the square root of that. That's what the calculation does for you. Yeah, so that's what the calculator does for you. So again, like, don't forget to be working on your little topic assignment.